We live kind of in very exciting times. I've been involved with solar energy from the very beginning with the very first panels off the ARCO plant. And we've already dreamed about passing grid parity, which means it's cheaper to do a solar installation than it is to make a coal-fired plant, for instance. And we've actually already passed it in many places, like all of the Hawaiian Islands, the whole Caribbean, most of Latin America. And so you would say, oh, well, that's good. Now they're all solar. Well, that doesn't work because there's physics behind that system. They have a hard limit. They're having a very hard, difficult time doing high integration solar above like 15%. And so that has to be dealt with. People have come up with the idea of the smart grid. When if you follow news, you see a few years ago there were all these glowing news articles talking all these wonderful things about the smart grid. If you keep following the news lately, it's gone sour because the smart grid wasn't implemented very well. These smart meters weren't so smart, and one of the big failings is how the data was dealt with. Now, when you start going into the idea of the smart grid and smart meters, you introduce a whole other element, the consumer, the homeowner, the general public, and now all of a sudden it's incredibly complex. And a lot of us, or maybe most of us here, are involved in the data business. And what makes the data business work isn't just that you've made good data structures and a good way to present it. There has to be a value there. There has to be something that makes it worth the money. And there already is a data business. And so they say, okay, we're going to double the amount of data. Well, that isn't necessarily going to double the value. In fact, if you increase the amount of data enough, it might actually lower the value because they have a harder time using it. And that's exactly what's happening with the smart grid, because rather than doubling the data, it could multiply it times 100 or 1,000. And there's really not a good way to use it effectively. So in order for us to move forward, it's so easy to get comfortable in our own realm. You really understand data structures and programming and all this stuff. But you really have to take into account physics of the system, combine it with a good data structure in a way to balance off local data versus the big data. And you have to take into account the customer. And you have to take into account the economics. If you can't do that, then you don't really have a path forward. So the solution that we work with is thousands of small, smart, autonomous systems. You're never going to have little dumb systems and millions of them and actually be able to control them. And you're never going to be able to have a meaningful user interface. The whole idea of, and you've seen all these ads, we've all seen them, somebody's got their iPad or their smartphone and there's a homeowner and they're looking at all the analysis of their data. But the reality is, the data has a latency. It's coming from some IP somewhere and has a latency of, 4 to 24 hours. And so it really doesn't have so much use. And so we have to move forward on that. So the whole idea is we've got to aggregate this thing into the different size blocks. So there's a lot of issues that have come up with, particularly the ones of you that are involved in high integration solar. That's been around long enough that there's some areas where it's already high enough levels where they can really measure this. And there's some parts of California, certainly in Europe, Germany and Holland, and a bunch of places have very high levels of integration. And they run into these are all very real issues. A lot of you people have dealt with these issues. And there's the utility issues. That's the one that people tend to focus on more because the utility companies are controlling things. They're the ones that are working. That's their problem. But the consumer issues are very real. These are things that they care about. These things that they maybe not understand very well, but they understand somewhat. They can tell if the lights are getting brighter and dimmer. They can tell if they don't have power. They spent $30,000 on a solar system on their roof and the power goes out and they don't have any power. So this becomes a very real issue. And as engineers, we're used to looking at data sheets. We understand, kind of how a transformer works and the different parameters you might change to design it. But who gave us the data sheet for the consumer? And they're a very big part of this puzzle. And so, and they're not necessarily based on hard logic. And it doesn't matter that they're not based on logic. They could be worrying about some little tiny Wi-Fi signal in their garage, and the mere fact that they're worried about it makes it a real issue. It's involved with the ability to deploy these systems. So you have to really understand it. They're very suspicious of the privacy and control issue. That's a very real part of the smart grid. It's a real stumbling block. The incidence of millions of people being out of power for several days at a time has risen very drastically over the last 10 years. And so the idea of having backup power and autonomous power is a very high perceived value by the public, particularly in certain areas, and these are all things that we have to take into account. And the idea, some of the consumers aren't just homeowners. Some of the very significant consumers are like cell towers, which there's massively deployed and they're geographically spread everywhere. These people are very sophisticated. The thing is, these people already have the budgets to pay for pretty much anything that we can implement. So it's kind of up to us to be smart enough to implement it. Part of trying to understand the physics behind this, there's some things everybody kind of knows the pieces, but they haven't necessarily put the pieces together. So the grid was designed where they had inductive motors and they had resistive loads. But we have a new kind of a load, an electronic load. The thing about a resistive load is if you reach capacity with the generator and the voltage dips, the current goes down. So it's basically a stable situation. But anything with a regulated power supply, meaning compact fluorescent lights, computers, all kinds, any electronics, means if the voltage dips, the current automatically goes up. What that means is if the reason the voltage is dipping is because you reach capacity, that means you're going to make it dip even more. In other words, you've created an unstable situation. Anything below that line is making the grid unstable. Like for an example here, here's 100% resistive loads. You put too much loads on, the grid reaches capacity, the current drops. Maybe the incandescent lights dim a little bit, but then when everything goes back to normal, it keeps working. It's a stable situation. With electronic loads, let's say 100% electronic loads, if you ever touch your limit of capacity for a second, it'll immediately collapse the whole system, because as soon as you touch it, it's going to increase the current. And the voltage is going to drop even more, and it just builds on itself. That time span is very close. That's way too fast to realistically communicate information from this guy's house all the way up to the grid and have the grid take some corrective action. So, of course, we don't have 100% electronic loads. But we already have 20%, and we're moving towards 70 to 80%. So this is becoming a real issue. So if you're going to design for tomorrow, you can count on this increasing. And there's another very interesting electronic load that a lot of people aren't thinking of like this. That's the grid tie inverters for all the solar panels. They are basically following the same thing. There's a set amount of power, and so if the voltage goes up, the way these things work is the voltage goes up on the grid, they automatically reduce their current. And if the voltage dips, they automatically increase their current because they're set at a set power. When you think of generator plants, like you could have two rotating equipment generating plants, and one is set, let's just to scale it, at 120 volts. This one's kind of set at 123 volts. This one's going to take the bigger amount of load. But when the total loads increase to a certain point, then this one's voltage will start to dip, and the other one will automatically share. It's kind of an automatic system. And actually, the more transmission impedance there is in the place, the more stable the position comes. When you have systems that aren't voltage sources, then you have like a constant power source. It's an inherently unstable thing. So what happens when this intermittent renewable energy comes and goes? Well, if they drop out unexpectedly, that's the easier thing to understand. Well, they have demand response systems, and they can respond fast enough. They can drop the loads. There are some demand response systems that I know of that are trying to hit 4 seconds. You can turn peaker plants on. Of course, that's going to take 10 minutes. If all else fails, you do have a backup plan. You can drop out sectors. You can have rolling blackouts. At least it does work, right? But things work in 2 directions. What happens if renewals come unexpectedly? Well, if you have a demand response system that has the capability to turn on loads, you could implement that. If you have battery, energy storage installed, you could charge batteries at that point. If you have peaker plants that are already running, you could turn them off. Of course, in that instance, you probably wouldn't have them running, and so that's not really viable. And so what happens if all that doesn't work? Well, you can't disconnect sectors. That's going to reduce the load on the grid and make it go up even more. So that is the fear that the grid companies can't ever risk hitting. And so what you have to do is they have to run at smaller and smaller percentage of their spinning capacity. And next year they're going to have to run at a smaller percentage because we're going to have more electronic loads and more renewable energy, which means they're less efficient. When they're less efficient, it means they're less profitable, which means they inevitably have to raise their rates. And when they do that, the customers perceive that they're doing bad things to them, and they think the smart grid is a bad thing. So let's look at the whole idea of the data processing. You've got a system here over on the left is what we've actually implemented so far. So they realize, hey, there's too many of these smart meters. We can't have so much data, so they've thinned the data out. So the smart meters are becoming less and less smart so that they can actually handle the data coming from them, assuming that the only value of their data is how it's used by someone up above. And so by making that data thin, there's still so much of it that they're not moving it around very fast. Like I said before, the latency of the data from smart meters is like 4 to 24 hours. What that means is it's useless from a real-time operational standpoint. So there's another way to think of this. And we've designed, we don't just think about it, we design and manufacture and implement the equipment to do this. And so the idea is you have very rich local data, richer than you could possibly imagine, right? Everything you could want to measure, you measure locally, but you put not just distributed data, you have distributed intelligence. So you put lots of intelligence there so it can make the decision and implement the decision locally. And so what you're sending up is highly compressed data. In fact, you can do the maximum theoretical compression of data, which is turn it into mathematical equations, send the equation once, and periodically send the coefficients. That's the name for that. That's what physics is. And you can get incredible value of understanding equations and graphs and things like that, and incredible levels of boredom out of enormous spreadsheets of repetitious numbers. And so the whole idea is to enhance the value, the meaning of the data. And you can also aggregate it into groups of houses. Just for example, 16 houses. So it's feeding into a Pi server, where it's aggregates 16 houses, and then maybe that goes up to another level where there's 16 of those systems. You got 256 houses aggregated together. What that gives the grid is it reduces their load of what they have to analyze and process, and number 2, it buffers the secrecy of the house. In other words, their paranoia of having, Big Brother always looking at knowing how much electricity it uses, God knows why they really care, but nevertheless, they do care, and they can have their security guaranteed at that level. And the speed that you could theoretically send that data, you could have your latency times, of a minute. to where there is something useful that could happen with that. So this is an example system. This is the equipment that we make, and we have systems working all over the place. This is what we're kind of basically planning on, recommending you could have in a home or a small business. The whole idea over here, you can see the 4 kilowatts of power modules. Those are actually like a UPS system. So they're hooked up to 1.8 kilowatts of solar, 6 kilowatt hours of batteries, and it actually can run your critical loads. So the refrigerator, the lights, the electronics are run on this, so they're like a UPS system load. There's enough solar and enough batteries to where the grid could fail literally forever. And they could limp along living in their house. They could have their critical functions. Now that changes an electrical energy emergency into an energy inconvenience, which is a major, major value, to no one else, to the government. And then you have that goes to the remote panel, and then through like a plug computer or a local computer where there's a PI data translator that translates it up and sends it up either through Wi-Fi or normal internet connections up to the next level. We're talking about statistically large numbers, so there's no reason for a dedicated network or anything. This can actually integrate things easily. It doesn't matter if a few houses come off the system because it's statistically insignificant. So the interesting thing here is this large black box. This is 6 relays into a box, and these relays control the big loads, the things that aren't on UPS. So when you have these loads, like your air conditioner, your electric vehicle charger, your hot water heater, big things like that, those things can be controlled now with intelligence. Now, the typical U.S. house has an average load of 1.7 kilowatts, but it has 100 amp service, which is 24 kilowatts. Obviously, there's a really big difference in those two numbers. They only need the 24 kilowatts because statistically, every once in a while, all those things could come on at the same time. But if you have intelligence, you can force them to take turns, meaning you could cut the 100 amp service to 50 amps. Which means for no perceivable difference of living in the house, you could cut the cost of the entire electrical infrastructure in half. We're talking about big, big numbers there. And then you can introduce more intelligence, so it says something like, don't run the air conditioner so much when no one's in the house, or something like that. You can knock about 20% of their energy out. One of the real problems with the smart grid is you promised all this value to the end user, but they never got any. All they got was a fancier bill, and their rates went up. So this is something that could actually give them value. Just to go this, you can go this later, but basically for about $12,000, that same exact system can be put in whatever number of houses you want. You look at 1,000 houses, it starts to be significant benefits that come off of that. Here's we have the translators already built and working into the Pi server. Here is a process book display of actual systems running. And of course, you could, click it again, and then you'd have that be a process book display of 16 houses of these together, or 256, or the state of California, or something like that. So it gives you the ability to really get this information, get your hands on it and have something useful right there. So one of the real key things here is the ability to aggregate this stuff. There's all kinds of benefits. Like I said, you have to think about the economics. And so what economic things are out there? Obviously, everyone knows that you can reduce your power bill by using less electricity. But a lot of people don't realize that you can participate in a demand response program, in a reactive power selling program, and a frequency stability program, because those programs are only available to people that are doing 100 kilowatts and up. But if you aggregate things, there can be companies that have a business model, and they're aggregators, and so they aggregate enough houses so they're well over that case. We're already working with a few people that's what their business model is. And so they all of a sudden, now you've got multiple revenue streams. You don't just have solar electricity and reduced electrical use. You have demand response. You're getting paid for that. And so that's all in place, and it's increasing. So imagine you're trying to stabilize the grid. That's the real problem. Think about trying to drive a car. If you're trying to learn to drive on a dump truck full of rocks, it's a way different experience than trying to learn to drive on a motor scooter. Because of the mass. When you steer a dump truck, you've got a lot of mass, big corrections. It's difficult to do that. A motor scooter is very simple. So the whole idea is, what would it take to drive? We all drive. You know what it feels like. If you could correct your steering once every 4 minutes, would that work? It wouldn't. Even once every 4 seconds, which is the fastest demand response system that's even out there, it's questionable. If you could do it every 17 milliseconds, which is one wave shape of a 60 hertz wave, you could drive real well. But with modern high-speed electronics, with local decisions, you can do that. Our systems already do that. And when you make the speed of the response much faster, what you're doing is you're reducing the size of the response needed to make something stable. And the size of the response is the size of the battery bank. And that's where all the money is. So this is a way to dramatically increase the effectiveness of a system while vastly reducing the capital expenditure. Now, if you're going to stay awake for one slide in the whole presentation, this is the one you want to do it on. This is very interesting. This is real data. This is what's really happening to the real power grid in Southern California with high integration solar. Now, this graph is expanded on the bottom part here, so that whole screen is about 10 minutes. And you can see I've kind of blocked off 1 minute there. And so you can see what the solar is doing. It's actually changing the voltage of the grid, because it's not always putting out the same amount of power. The sun's coming and going. And this is like real stuff happening. You can see that, within a few seconds, you need to be able to respond. Now, the typical solution that's being implemented today in the world is to spend high amounts of money on peaker plants to deal with this issue. A peaker plant takes that entire graph to even turn on. A peaker plant can't even come close to doing there. Whereas, like the equipment we do can actually charge the batteries when the voltages are going up and discharge them when it's going down. And so that the actual amount of time that it's doing this battery balancing is like only a couple minutes at a time. Meaning the amp hours or the kilowatt hours that you're actually taking in out of the batteries starts to become insignificant. In fact, you could actually do it with ultracapacitors. Keep in mind here, when that voltage is dropping rapidly, all of the grid tie inverters, which are the thing that's making this happen to begin with, are seeing the voltage drop, which means their current goes up, which makes the voltage drop even more. And the same thing happens the other direction. When they see that voltage rise real quickly, they automatically reduce their current. And so so in other words, they're creating more instability. And we're talking about many megawatts of solar coming out here that are basically designed to make the system unstable. So we can do this locally. To do this, and maybe a lot of you don't think about peaker plants so much, but that's the dominant solution out there. Trying to use a peaker plant to address this issue is kind of like if you wanted to adjust the angle of a fly's wings during flight and you decided to use a jackhammer to do it with. If you have a vast, squandering of funds with a very low likelihood of ever dealing with the problem. So this is a graph, emerald graph. Probably a lot of you have seen that before. That's over 24 hours. That's kind of typical use pattern for a whole grid sector. The whole idea here is they're worried about this red line's the forecast wind. Same would be for solar. And the black line is what really happens, and it costs them more money, the grid companies, when it puts out more or less. In other words, they're never satisfied. And so they're proposing multi-million-dollar energy storage facilities. But if you scale this to one house, that whole graph is only 2.7 kilowatts high. These little corrections are only 300 watts. We got 4 kilowatts of power modules in there. We're only dipping into less than 8% of the battery capacity. You can completely address this issue. So the whole idea of doing it small with local intelligence really has a lot of value. But the whole idea is you got to have distributed intelligence, not just distributed energy generation. You have to and so this is the same basic graph here. But this is just, the whole basic idea. There's the solar panels output, and you can see if you charge there and discharge there, what you can deliver to the grid is flat. What you can do is you can return the grid to something that's more like what they were designed for, like the world of the 50s, where what they do is they specialize on economic production of electricity, and that's what they do. They sell that, rather than having them try to correct for all the intricacies of each house or each neighborhood, which they were never really designed to do that. It's not reasonable to expect them to do that. Here's an example. This is actually from Costa Rica. This is a state-of-the-art, modern, recently installed peaker plant. This is one, actually, it has 11 turbines in it. And it cost $360 million to install that. Well, for that same amount of money, they could have put this system into 31,000 houses. Now, that would have produced a system that could produce 124 megawatts to stabilize the grid, whereas the Garabito is a little more. It's 200 megawatts. But this also includes, in that price, 57 megawatts of solar. It includes a smart demand response that can save energy of 249 megawatt hours a day. You combine the solar with the smart demand response, they could save 183 gigawatt hours per year. And they can respond in 17 milliseconds instead of 4 minutes. So if you look at the value proposition of that, we're talking about the same amount of money. We're talking about a return on investment of 1 day. So what basically we've reached here is we haven't reached grid parity everywhere, but we have reached peaker parity everywhere. Everywhere they're thinking about putting a peaker plant, which is everywhere they're integrating renewable energy, they could get more bang for their buck out of installing small distributed systems, just lots of them. Here's an example. This is a typical example now for the United States. This is a natural gas-fired peaker plant. Okay, say 50 megawatts. It's going to cost them $75 million to install that thing. Well, instead, they could do 50 megawatts of peak power out of the system that I already outlined. As an example, that'd be 12,500 systems. Well, that'd give them the same peak power, but now would have an addition of 23 megawatts of solar power integrated with 98 megawatt hours of energy storage, which is considered major in today's energy storage market. Somebody says they got a 98 megawatt energy storage facility. They'd be the only game on the planet, actually. They have demand response included, thrown into the deal of 50 megawatts. Not only demand response, but automatic high-speed demand. Demand response that can respond within 17 milliseconds, which is not even existed on this planet. So the actual amount of electricity it's producing is significant. Your peaker plants are averaging, 1 to 10%. So I just picked 5%. And that is, if you do 5% once a day, you're going to discharge your batteries by 61%. But that's if you just do it once a day. But the real use patterns, it'll be spread out over several times. And so if it was twice a day, it'd be 30%. If it was 4 times a day, it'd only be 15%. So you're starting to get into the area where your batteries are going to basically, last a really long time, and it's a really economical use of the batteries. One of the big deals is it's bidirectional. All the peaker plants all they can do is insert energy. They can't take energy out of the system and turn it back into natural gas. And that's essentially what you're doing here with a system like this. You're putting it back into the batteries. And so it's bidirectional, and that's a major thing. This also includes electronic power factor compensation. But this system costs more, $145 million rather than 75. It's like, twice as much money. But there's solar revenue. If you work out the simple ROI, it's 9 years. But still, people in this industry are willing to think about a 9-year ROI. Not only that, this has all this green stuff. It's not making any pollution. It's solving the problem. It's making the grid stable. It's actually returning the grid to a more profitable situation because they can run at a higher percentage of their rated capacity. They can run at the, that's where their money is. But since we're so much faster, and since we're bidirectional, a more realistic approach... Oh, yeah, right. That's not the computer. Is this one, where we do the exact same installation cost. For 70, now you can't do as many houses. Only 6,478 houses. It's only doing 26 megawatts of peak power instead of 50, but it's doing it super fast. And it's including the 12 megawatts. It's bidirectional. This is more realistically what could really happen. And of course, that gives you a return on investment of 1 day. It's the same installation cost, yet you have all this green stuff. So there's really no reason not to do this. It, of course, requires intelligent, high-speed electronics, but that's what the world can economically produce. That's, of course, what we do. So, thanks.
Well, I can count on Lee. Thank you.
I think there's one more that we're missing here on because the infrastructure to do not just the peaker but the smart grid is that whole infrastructure cost that goes in from the utility side to manage versus because you've got intelligence distributed, a lot of that bidirectional communications and all that infrastructure, the IT infrastructure, whatever, fiber, et cetera, goes away.
Exactly. To tell you the truth, the smart meters become redundant at this point because everything that a smart meter would produce is already included in this system. But this system isn't, for instance, the example for Costa Rica, that would make to make that entire country carbon neutral, you would put this in about 1 out of 20 houses. Now, I'm expecting to completely eliminate the peaker plant function in the United States would be about 1 out of 10 houses. So, in other words, you're not getting data from every house. You're getting houses from 1 out of 10 houses. But what does the grid need all that data for anyway? I mean, if you have a sampling of 1 out of 10 houses, you're getting, a pretty good statistical feel for what's going out there in the field.
So one of the questions I often ask Hart has to do really with the earlier points that he put up there for the disruption of the what I would call the dumb inverters and solar systems on your networks out there. So you've all probably dealt with those of you in the Sun Belt for sure have dealt with some of these problems already. I'm certain. I guess just a couple points you should comment around how the stability problem goes away. I mean, some of the problems are like reverse flow of the energy, some of the things around fuse coordination and some of those things. Maybe you have a couple comments on that before we get in?
Well, what we've done, this gets a little bit into the technical electronics, but like I pointed out before, a generator, a simple spinning generator, is a voltage source with an impedance. And so, if you take less power out of it, and eventually it could put out no power and keep spinning and keep making that voltage. What we've done, which is different than any of the other inverter companies, is we've created a high-speed electronic voltage source. In other words, we've emulated the peaker plant. But what we do is we can high-speed change the parameters so that we can basically, even within a wave shape, change the patterns so that it does what we want. So it's inherently more stable. Now, if you had peaker plants that were bidirectional, they would be unstable because you could have 2 peaker plants or 2 generating plants, and this one could power this one and this one could take it away. They could have things going back and forth. The reason that they're stable is because they're one directional. And so our equipment is potentially bidirectional, and we, with logic, force it to be at any given moment one directional, so it stays stable. So making it a voltage source, if you think about engineering models, is a much more stable situation. It removes the problem, is what it does.
So we have to be very precise about our timing here because these guys have to reorganize the room for us. They have set rules around doing that stuff. We're going to return here by 1:30, correct? And lunch again is at the Golden Gate at the